everyone, this video is going to be about continuity and continuous functions at certain points. We will get into the intermediate value theorem as well as implicit differentiation soon, but for now just continuity and continuous functions at some point C. So a function is called a continuous function at some point C. Function g of x, excuse me, is called a continuous function at some point C if all three of these things hold. So firstly, that g of c exists if the point cannot be used in the function and produce a value, then you can stop right there. You are not going to have a continuous function. Second, if the limits as x approaches c of g of x exists. And thirdly, that the limit as x approaches c of g of x is equal to g of c. So g of c exists and the limit as x approaches c of g of x is equal to g of c. So we're going to quickly do some dual page display here, and we're going to talk about this. So I have our definition on the left, and here's some example functions on the right. So y equals the absolute value of x. Let's see if this function is continuous at its most interesting point, x equals 0. Well, let's say c, in fact. C equals 0. So if you throw 0 into the absolute value, you get, so we'll be testing A here. You'll get the absolute value of 0 equals 0. So this exists. So we're going to check this off. This works. It's got the green light. Now let's talk about B. Does this limit exist? The limit as x approaches 0 of the absolute value of x. Well, let's think about it. If you're approaching from the left, as you approach 0, you go from positive values and you approach 0. So that would be approaching from the left. You're going positive and you're approaching, approaching, approaching. You get to 0. Good. Okay. And now if the right-hand limit agrees with that, then this limit does in fact exist. Well, we're approaching, we're approaching, we're approaching, and we're approaching 0. So both of these limits agree, which means in fact that the two-sided limit, which is what this is, exists. So we're happy. And finally, we can tell that this limit b is 0, which is the same as what we got in A. So this limit equals 0, which is equal to the absolute value of 0. So we're all set there as well. So the absolute value of x is a continuous function. Now let's look at y equals 4x cubed. There's another example. Let's go with the point of interest being 0 again. So we can say for A, does this point exist? Yes, because we can say 4 times 0 cubed is equal to 0. So it spits out a real number. We're happy. It exists. Now let's talk about B. Well, again, the left-hand side, so the left-hand side on the graph is approaching 0. The right-hand side on the graph is approaching 0. So the left and right-hand limits agree, which means that this limit as x approaches 0 of 4x cubed exists. And its existence is part B. And then finally, we see that this limit is equal to 0. So C is done for us. Make that a green check. Okay, so let's talk about this next page. This page has some examples of discontinuous functions and what they look like. So I'm going to make this one a little larger for the time being, but I will soon flip these around and make it okay again. So here we have a function that's a piecewise function, and it has x squared is the value when x is not equal to 2, and 5 when x is equal to 2. So right off the bat, we see that a, in fact, holds here. So a will get a green check because at x equals 2, we're looking at this limit as x approaches 2. So at x equals 2, we have a value, 5, so that works. Now b, well, the left-hand side is approaching 4, and the right-hand side is approaching 4. So b, in fact, also works here, because this limit exists. The limit as x approaches 2 exists, and this limit is equal to 4. So let's write that down. So we have the limit as x approaches 2 of f of x is equal to 4. So that exists, and that's fine. Let's talk about c, though. The actual point, when you plug in 2, well, we have f of 2 equals 5. Well, so let's move this. F of 2 equals 5, but the limit, I'll get this out of the way. So f of 2 equals 5, but this limit here is equal to 4. So these limits, this limit does not equal this function value, so c is violated, and this is a discontinuous function. Now that's pretty clear from the graph itself, but that might not be super clear from just the function, why it is discontinuous. And it's because it violates part C. All right. Next, let's bring this function here up. This function in the middle. This is going to be, wow, I brought a parentheses. F of x is equal to 1 over x minus 2. So right away you guys might see a problem here. If we're looking to see if f is a continuous function at x equals 2, well, let's think about it. Let's try to throw in 2. So 1 over 2 minus 2 equals f of 2. That'd be 1 over 0 equals f of 2. 1 over 0 is not a real number. So that's our problem there. Another interesting portion of this, so this automatically eliminates this from being a continuous function at x equals 2. But let's look at another portion of this. So really for part B, if we look at the left-hand side is approaching negative infinity. It's getting as small as it can. While the right-hand side, as we approach 2, is getting as large as it can. And so this limit, the limit as x goes to 2 of f of x is in fact going to give us nothing, no result. So A and B here are both violated, and clearly this makes C impossible to satisfy. All right, finally, let's look at this function here. This function does not violate B, because as you can tell, we're both going towards infinity from both the right and the left, so these agree, but it does violate A still. So 1 over 0 gives us a big fat frowny face. All right, so finally I have attached some, So finally I have attached some AP problems to try. So pause the video on any one of these problems and you will be able to try it at your will. Also, I will attach a PDF so that you guys are able to attempt these problems if need be. This is by no means a requirement. Thank you for watching.